Hello students, welcome to Math 3410 Differential Equations. In Lesson 1A, we're going to cover only the preliminaries. In the first video, we covered Section 1, Complex Numbers, which came from Algebra and Trigonometry, and I think a lot of students decided to just skip it. That's okay. Now let's go over to Section 2, Transcendental Functions, and these are coming from Calculus 1 and 2, so they may be a little bit more worthy. Here we go. Let's begin with exponential and logarithmic functions. There are two ways to define exponential and logarithmic function. Excuse me, I take it back. There are many ways, but two of my favorite ways are these two. First, define the exponential function using Taylor-Maclaurin expression, like this, and then define the logarithmic function as its inverse. This is my favorite way because this definition of exponential function can be extended over to complex numbers, square matrices, and so on and so forth. Any kind of commutative algebra, we have this. There's a bit of a work here, by the way, because whether this expression is really a one-to-one function or not is not as clear as the other method. It does turn out to be a one-to-one function because it's strictly increasing, but if you look at each individual factor here, each individual term here, all the odd terms are increasing, so they're okay, but all the even terms, those are U-shaped, so it's not clear that this is indeed an increasing function, but it turns out that way. Consequently, we can use the invertibility and define the logarithmic function as its inverse function. Here's a visualization, by the way. Exponential maps negative infinity to 0 to infinity. So domain goes forever, and this graph goes to the right forever, of course, and then it'll explode upward, but never go below or hit y equal to 0. So this is the range, and that's the domain. Now, if you take the inverse function, logarithmic function is valid only when x is greater than 0. So this is the domain. So range becomes domain, and then the domain becomes a range. You can see those from here. Another definition is this. Define the logarithmic function first using the definite integral here, and then define the exponential function as its inverse. Does it work? Yeah. And this one over here, we're taking definite integral of a positive function, 1 over t, and x is always greater than 0, so yes. So clearly this is an increasing function. So invertibility is just triviality. So that's an advantage, but there's a disadvantage here. We can define any real function like this using the definite integral like this, but I cannot expand the same idea into complex numbers or anything more complicated. So there is a trade-off. It's okay, and this method is certainly valid, but the method I prefer is this one. As for the gap, think about it. Can you actually prove that this expression is strictly an increasing function so that the inverse exists? Can you prove it? Not just by looking at the graph, but can you actually prove it? That's my challenge. And then let's go to the next topic. For arbitrary base, these are the definitions. Now, do not consider these as change of base formulas, because these are definitions of exponential and logarithmic functions, which came from natural exponential and natural logarithm. For other bases, we have to define it first, and this is the way we're going to define those. All right, next. Exponential and logarithmic rules. We're going to discuss only the first one, and that's going to be a work. The others, I'm going to leave those to students. If you have this is not going to be difficult to prove because all you have to do is flip this denominator to the other side, and then you have multiplication, so you can use this to prove that. No problem. A detail is left to the students. How about this one? This is nothing more than a trivial application of change of basis formula here. You see, this one applied over here because this is my A. So it turns out to be a simple exercise as a matter of fact. Now how about these three? As a matter of fact, these three corresponds to the exponent rules over here, here, and there. And using these three, you can deduce the other three. That's going to be a bit of a work, yes, but I'm going to leave the details to the students. Now the first rule. Okay, let's do it. No, I take it back. No, not yet. Let's postpone it because this is going to be a challenge, and let's talk about the differentiation rules first. The derivative of exponential functions stay the same, and derivative of log function is 1 over x. How do you prove the first one? Well, you can always go back to the definition of the exponential function here, and then you can define from there. We can prove it from there. So, and then this is like this. And then instead of writing like these, let me write it as 1 and then 1 factorial, and this one 2 factorial, and 6 is 3 factorial. That's 4 factorial, 4 times 3 times 2 times 1, and that's 5 factorial. Let's do it like that. And then if we take the derivative, what happens? This becomes 0. And then this becomes just 1. And this becomes 2 comes out and then simplifies. So x to the first power divided by just 1 factorial remains. And then take the derivative. Multiply by 3. 3 and 3 factorial cancel each other out. So we have x squared and then we have 2 factorial. We have 3 times 2 times 1, but 3 is gone because of this multiplication by 3. Next, multiply by 4 and subtract 1 from the power. And 4 and 4 factorial cancel, and then we have only 3 factorial left. And what we have the original. This is the legitimate proof, as a matter of fact. Yes, we can do this, but I'm gonna take a little bit different step here. And the primary reason I'm doing it this way is to show you a very, very typical technique that we are going to be using a lot in this course. Okay. So from the Taylor expansion here, 1 over k factorial, x to the k power, okay. And then here, let's divide the summation into 2 parts. K equals to 0 term and the rest. This is very, very typical trick. Separating the sum, first several terms and then the tail part. So here, I'm simply taking only 1 term here. 0 factorial is 1. 0 power is 1, so we have 1 here. And that's going to become this one. So far so good. Oh, actually, no. This corresponds to that. And upon taking the derivative, it'll become 0. So far so good. Now, how about this summation? Here's another technique that we are going to be using over and over again toward the end of the semester. This begins from k equals to 1, 2, 3, 4, and so on, and change it so that it begins from 0. K is going from 0, 1, 2, 3, 4, and so on. But let's replace those k's into k plus 1, so that when k begins from 0, this k plus 1 goes 1, 2, 3, 4, 5, and so on. So k is going from 1, 2, 3, 4, 5, 6, 7, and so on, versus k plus 1 is going from 1, 2, 3, 4, 5, 6, 7, 8, and so on. They're exactly the same. So this expression and that expression are actually the same. Look a little bit confusing because beginning from 1 versus 0, and we have k plus 1 versus k. A little bit confusing, yes, but better used to it. You had better get used to this. We're going to be doing this a lot in this course. Okay. Now that we have these, let's take the derivative. 1 becomes 0. And this summation, k plus 1 comes out. K plus 1 k factorial. Cancel, and we have 1 over k factorial. And k plus 1 minus 1, so we have just k power. And what is this? That's Taylor series expansion for e to the x power. And that's what we get. So this proof here versus that proof down here. Everybody will think the proof down here is easier to understand, and I agree. But this kind of technique is necessary in this course, and that's why I took a detour. How about the second formula here? That's easy. That's nothing more than an implicit differentiation. Y equals to log of x, and then that's equivalent to e to the y equals to x, and then we simply take the derivative implicitly. Exponential functions stay the same, and by chain rule we have dy dx, and the derivative of x by x is 1. So what do we have? We can solve for dy dx, and that's the solution. 1 over e to the y power, and e to the y power is x, so we have 1 over x. Okay. And then these two derivative formulae, I can leave those to students. All we have to do is to recall the change of basis formula. Here, use this to transform this one into a natural exponential function, and then apply the chain rule. You're going to get that. And as for this logarithm, changes to that logarithm here, and then apply the derivative rule. You're going to get what you want. The details are left to the students. Okay, that leaves only one remaining problem here. And that's going to be a challenge. Is everybody ready? Okay, here we go. Here's a preparatory step, a binomial theorem. X plus y to the k power turns out to be this sum, binomial sum. Basically, it's k choose r. So out of total k, we select r slots for x, and the other k minus r will be y, and that's basically what this is all about. Let's see. X plus y, x plus y, x plus y, dot, 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 another x plus y. There are k such vectors. And how many different ways to get x to the certain power, y to whatever power? You're making this selection. From the first vector, you have to select either x or y. Here, we have to select either x or y. Here, again, we have to select either x or y. And so on. In the end, out of k vectors, let's suppose I select x r times, and the other k minus r times I selected y. And that's how I'm going to get x to the r power, k to the k, y to the k minus r power. So this is combinatorial problem, and you're going to end up with combination k choose r. And that's basically it. And here I decided to go to in descending order. I started from x to the k power first. Here something is not right. No, nothing's wrong. Nothing's wrong. Excuse me. Excuse me. R is going from, oh, no. Let's correct it. K minus r power and r to the y to the r power. Okay, that's right. R is going from 0 to k. So we start from r equal to 0, y to the 0 power, and then first power, second power, all the way to k power. Okay, all right. Now it's everything's. And then each coefficient here is combination. K choose r, k choose k, all k is going to be x, and k choose k minus 1. K minus 1 of them is going to be x, the other one is y. K choose k minus 2. Out of total k, k minus 2 x's, and there are 2 y's, and so on and so forth. So what do we have? We have these binomial coefficients. These. Those are combinations. Okay, all right. Remember this binomial theorem, and then let's go ahead to this formation. E to the x power times e to the y power. Here we go. E to the x power times e to the y power. Now, let's break those up. How do we get 0 power? This times that. That's the only way to get 0 power. Next, how do you get the first degree? First power times 0 power. 0 times first power. So we get this. How do you get the second power? Second power times 0 power. First power times first power. And finally 0 power times the second power. So we get the second degree terms. How about the third degree terms? Just one more time. Third power times 0th power. Second power times the first power. First power times the second power. Finally 0 power times the third power. We're going to get this. In general, kth power times 0th power, k minus 1 power times first power, k minus 2 power times the second power, and so on, and we're going to get this expression. Now, how do you manipulate each? Here, x plus y, so we have just x plus y, no problem there. Here, x squared, y squared, and then middle, I need 2 factorial down here, but I only have 1, so we have to multiply 2 to both numerator and denominator, and that's how we get this 2. So we have complete square in the numerator, so this total thing becomes x plus y total quantity squared over 2 factorial. How about the third powers, these? Well, I need 3 factorial for common denominator. Okay, 3 factorial. And here I have 2 factorial, so I have to multiply by another 3. 2 factorial, I need another 3. So multiply by 3 here, multiply by 3 there. And what do we have? Pascal's triangle. We have complete cube. So this turns out to be this, x plus y cubed over 3 factorials. In general, we're going to be using binomial. Let's look at this. We need k factorial as common denominator, so we need k factorial, divide and multiply by k factorial. This one's already okay, we have it. Divide, multiply, and so on. So we can artificially generate k factorials down there all the way, so that we end up with k factorial in denominator. Now, how about the other coefficient? K factorial over k minus r factorial times r factorial. Wait a minute, this is binomial coefficient. The combination k choose r. K choose k minus r equivalently. So all this is binomial, x plus y to the k power by this binomial theorem. So what do we have? We have the Taylor series expansion, 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial, and so on in denominator, and numerator, x plus y to the 0 power, first power, second power, and so on. We have e to the x plus y power. That completes the proof. The other formulas can be deduced from here, and I'm going to leave those to students as an exercise.